Let me start recording. So the first topic that we're going to do in physics is we have to define what are physical quantities, what are units, and what are some of the things that we can use to measure those physical quantities. Because, you know, physics is all about a science of dimensional analysis. So these are the objectives that we're going to have to accomplish in today's lecture. So we first have to learn how to use and describe the use of various measurements. For example, measuring cylinders to find length or volume. We have to describe measurements of time. And we also have to be able to obtain small distances using something known as a simple pendulum. But this is a long lecture. It's actually over, how many slides do we have? It's actually over 43 slides, but I'm going to end on the simple pendulum, then I'll combine it with vectors next time we do physics. We'll also learn how to use things like Vernier calipers and also micrometer, screw gauge. All right. So practically, let's first start by defining what physics is. So for me, I like to define physics as the science of measurement. And what are we measuring? Let me highlight. Okay, so all right, so physics so physics, all right. Okay. All right. All right, so physics is practically the science of measurement, because remember in our introductory lecture to physics, I said that for physics, you just have to learn how to say just one or two things, because it's all about measurements. And what are you measuring in physics? You are measuring things known as physical quantities. So physics is the science of measurement. And what are you measuring in physics? Those things that you're measuring are known as physical quantities. So practically, a physical quantity is just a measurable characteristic of that object. So in physics, we measure physical quantities. And these physical quantities are measurable characteristics of a given object, physical quantities. So example of physical quantities, you may board a bus or you might move in a vehicle. That movement is known as distance or displacement. That's a physical quantity of length. There was a certain duration of that journey. We can measure that duration of that journey, that time interval, using the physical quantity of time. Every object that we have has a certain mass. That's a physical quantity. Weight also. If you are on the stove, you feel a certain physical quantity of you feel some thermal energy, you feel heat, and that physical quantity is temperature. So this is practically what physics is. It's trying to make sense of the natural world through measurements. And what are you measuring? Physical quantities. And always, I'm telling you this in physics, this is extremely important. Every physical quantity is going to have a numerical magnitude and a unit. What do I mean when I say every value in physics is going to have a numerical magnitude and a unit? From now on, when you hear the word magnitude, magnitude in physics will always, or mathematics, magnitude will always mean the size. It may be a vector, it may be a scalar quantity. We're going to be able to define those terms when we look at vectors and scalars. But everything that we measure in physics has to have a magnitude. Remember, magnitude means size. So please, all the time you have to include the size and the units. If you don't do this in physics, your answer is going to be extremely wrong. If I say 25 kilograms, this 25 here is the magnitude, and the kg will be the international system of units, the standard SI units. So all physical quantities, by the way, mass is a scalar quantity. Let me just say this for now. Mass is a scalar quantity. It means it just has size only. No one goes to the shop and say, let's go buy a 25 kg bag of mini meal due east, due south. We don't say that, right? Because mass is a scalar quantity. These are physical quantities that only have size only without direction. But when you are in a vehicle, you might say 40 kilometers per hour due east. So this will be an example of a vector quantity. And remember, it has got a magnitude and a numerical value. So that's a unit. And later on, we're going to discover that something like a speed is a derived quantity. It's a derived quantity. It means it's made up of two other fundamental units, mostly kilometers, this is length, and hours, this is time. So in physics, we also have basic units and derived units. We're going to talk about that. So here, that's actually the third point. So to recap, in physics is the science of measurement. And what do we measure? We measure physical quantities. Physical quantities are the measurable characteristics that an object possesses. And all these physical quantities are going to have magnitude, which includes the size, and the unit, the numerical value, so that we can make sense of that. And these physical quantities, some can be scalar quantities and others can be vector quantities. The scalar quantities only have size without direction. 25 kg bag of mini meal, not 25 kg due east. We don't say that. But we can have certain vector quantities. For example, speed, we can say, or velocity or acceleration or force. We can say 40 kilometers due east, or we can say 200 newtons to the left. Imagine you push an object and you push an object with mass with a certain amount of force with it, and it moves, and the resultant force is 200 newtons to the left. So force is also an example of a vector quantity. So that's what physics is all about. So remember, the magnitude or value of a physical quantity is always written as a number followed by a suitable unit. So like this 25 kg here, there's a number there, 25 is the number, and the numerical unit there, the SI unit, the international system of units. From now on, certain questions will want you to always give your answer in standard SI units. So in physics, be very careful. If your answer is not in SI units, before you solve, you have to make sure that all the units are the same. You cannot solve time in seconds with time in hours that you start multiplying or dividing like that. The first thing you have to make sure is, are my units in SI units? Are my units all the same before you can convert? And also in physics, you have to know your formulas. I actually recommend maybe in your physics textbook, try getting highlighters. Remember, I told you to get a highlighter. I like using highlighters when studying. When you get your highlighters, when you start finding equations, we talk about maybe velocity, we talk about Newton's laws and force. Always highlight those equations, because in physics, we do something known as dimensional analysis. Remember, you have to know this terminology, by the way. I'm not telling you this to punish you, but I'm telling you this so that you know the language of physics. Once you know the language of physics, everything is going to be easy. So dimensional analysis. Someone might say, all right, force is mass times acceleration. And another person can say, all right, density is equals to mass over volume. I'm going to teach you how to change the subject here. How to change the subject. So imagine we are trying to make mass the subject of the formula. I'll make density into a fraction, dividing it by 1, then I'm going to cross multiply. Therefore, mass will be density times volume. But force is equal to mass times acceleration. So from here, I can substitute in this equation. The new equation becomes force is equal to density times volume times acceleration. And you can do certain manipulations. So here where you're trying to link each formula, where you're trying to manipulate all formulas, is known as dimensional analysis. And when it comes to physics, you have to make sure you sort of read and understand the question, because physics is like it's a sort of puzzle piece. Once you read and understand the question, you can scan through it, get the clues, collect the data, make sense of the question, find the right equation, principle, and formula to use, and you'll be all right. As long as you know how to read and you remember the questions, and you remember the formulas, you won't be able to fail a single question in physics. All right, so I did give an example of this. So I said a physical quantity is a measurable quality or characteristic of an object. For example, the physical quantity of weight, mass, kg, distance in length, space occupied by an object area, and temperature of the room in Kelvin. But I want us to understand certain fundamental quantities. So our entire syllabus, we're going to be studying things known as base quantities. Base quantities. Base quantities are also known as fundamental quantities. It means all other units come from these very, very essential base quantities. So these are the base quantities. We've got mass, length, time, temperature, and sometimes they can bring a table like this. They can bring a table like this, and they might say, they will say base quantity, base quantity, and they might say maybe symbol, and they'll say SI unit. Then they say maybe fill in a table like this, because remember, base quantities are the mother units of all other physical quantities. They might say mass, length, time, temperature. Maybe they'll also say something like luminous intensity. Luminous intensity. And they will say, all right, what is the symbol of mass? We are going to say, all right, mass is a small letter m. And the standard SI unit is a kg of mass. Length, small letter L. Standard SI unit for length is meter. Meter, capital letter M. Then time, you say time in seconds. Symbol, small letter S. Temperature is actually measured in Kelvin. So the symbol for Kelvin is K. So you say Kelvin. And luminous intensity is measured in Kelvin. Although we don't use luminous intensity, but the examiners see a symbol CA. Examiners might bring this to just throw the students off. They'll be like, what's this luminous intensity? Let's just bring it. Sometimes they'll also bring the more symbol MOL, so more symbol MOL. This measures the amount of substance. So that's the SI unit. We're going to encounter this one in chemistry. So with all these fundamental SI units, mass, length, time, temperature, luminous intensity, we can derive all other units in physics. And because we're deriving all other units in physics, we can have derived quantities. So derived quantities are quantities that are derived from all other units. So let me give you examples of certain derived units. For example, area. Let's start with area. Area. So area is defined as the space. As area is how do you define area? Volume is the space occupied by an object. I can't remember the definition of area as such. Perimeter is the distance around a given shape. Volume space occupied by an object. All right. And well, let me give an example of area. Area of, let's say, a two-dimensional figure like this. Let's say this is a rectangle. A rectangle. Two-dimensional figures. It has got a length and it also has breadth. So we say area is length times what? Breadth, right? Length is distance, meaning length, because distance, the SI unit is meters, right? Small letter m. Length is measured in meters because it's a distance. So we'll say meters as the SI unit multiplied by the breadth is also measured in meters. So we'll also say meters there. That's my case. We'll also say meters there. Therefore, area is measured in meters times meters to be square meters. So this is the unit of area. Area is measured in square meters. Meters, so this unit here, square meters, has been derived from a fundamental unit of length that's measured in meters, so square meters. Do you see how we've been able to derive the SI units of area, square meters, by from one fundamental unit, which is distance measured in meters. Let's take another example of volume so that you see what I mean when I say all fundamental units. We can use fundamental units to derive other types of units. Let's take an example of volume, the space occupied by an object, and we take an example of a cube of some sort, some form of wooden brick cube. So a cube is a three-dimensional figure. A cube will have length, breadth, and height. And remember, distance, the SI unit for distance is always in meters, right? Small letter m. So volume is length times breadth times height. All these, length, breadth, and height, they are measured in meters. So therefore, length would be meters times meters times meters. Therefore, the SI unit for volume will be cubic meters. Do you see that? So we derive the SI unit of volume using a fundamental of base unit. Let's take another example of speed. Speed. So the formula for speed, we can say speed is speed is equal to distance over time. The SI unit for distance, remember, is meters, right? So meter over the SI unit for time is seconds. Exactly, amazing. So the SI unit for speed will be meters per second. So this is the SI unit for speed, derived from two basic fundamental units: distance, meters, time, second. You derive an SI unit for speed, which is meters per second. The last one, force. How are we going to describe some units for force using our fundamental units? So force is mass times acceleration. Mass is measured in kg multiplied by acceleration. Acceleration is the rate of change of velocity with time, and it's measured in meters per second squared. So therefore, where there is acceleration, we put meters per second squared. So this here, kg times meters per second squared, is the SI unit for force. SI unit for force, but we don't say it like this. We just simply say this as newtons. So newtons, 1 Newton is 1 kg per meter per second squared. So this becomes the SI unit for force. Where did it come from? It came from a basic unit of mass and acceleration here, which is made up of two basic units of distance and time squared. So this is what I mean by, if you know your fundamental units, you'll be able to derive any other type of unit in physics. So you also have to know, I will require you to sort of, these are more examples of derived units, so it's fine. This table, know it, please. It will come in the exam. Know this table. So when I send you the notes, make sure, and the video, make sure you study this. Know this table. It can come in either paper 1, paper 2. You do not want to lose marks, so you have to know your basic fundamental units: length, meter, small letter m, mass, kilogram, kg, time, second, temperature, Kelvin. Please, not degrees Celsius, it's Kelvin. Current, when we do electricity, ampere, capital letter A. Luminous intensity, the one I was telling you about, candela, CD, and amount of substance, which is mole, symbol MOL. Know this table. It's very, very important for your exams. You do not want to lose marks, so you have to know this table. All right, so prefixes. So at times, measurements are extremely big. So in order for us to make sense of those measurements, we use prefixes to convert something that is an extremely big unit into something that's a little bit more compressed. So prefixes are a little bit like a standard form. We're going to look at standard form and significant figures very, very soon. So for example, you can say what can I say, 1,000 kg, 1,000 kg, or I can say Actually, let's try something bigger. Let's say 1 million kg. Instead of saying 1 million kg, you can say 10 to the power 6 kg. So this 10 to the power 6, we will know that, all right, 6 zeros means a million. So it's a form of a standard form, but using a given power, right? 10 to the power 6 means it's 1 million. So that's the whole idea behind prefixes. You're trying to sort of get something that is big and try to compress it in a manner that can sort of make sense, because we have no time of writing all these zeros in a given figure when you can just say 10 to the power 3, 10 to the power 6, 10 to the power 12, etc. So that's the whole idea of prefixes. And prefixes also help us, they help us to convert units. So let's say we have 10 kg. If I want to convert kg to gram, I'll just say, all right, kilo is 10 to the power 3. Therefore, this would be 10 times 10 to the power 3 grams, meaning this would be 10,000 grams. So the prefixes also help us to change units. No wonder you really, really have to know your prefixes, because it will be very essential for you to convert units in a given question. So here's another table for you to know, unfortunately, because as you're going to see the application of this table when we start looking at all these other topics, kinematics and dynamics, motion, Newton's laws, mass, density, mass and flotation, momentum. When we look, even electricity and so on, when we look at all these topics, it will require us to always make a unit conversion from kilometers per hour to meters per second, from hours to seconds. We'll be required to change time, and this table here of prefixes is going to help you change those. So know this table, at least know the basic ones, like know the basic ones. For example, this one here is deci, 10 to the power -1, centi, milli, micron, and nano. At least know these, because these are the ones that are usually common in the exam. Deci, centi, milli, micro, sometimes nano. So at least if you know that, all right, a centi is 10 to the power -2, you can easily convert 20 centimeters into meters, because you're going to say, all right, this centi is 10 to the power -2. So it will be 10 times 10 to the power -2 centimeters, which will be 20 multiplied by 1/100. I'm going to show you why this will make sense. When I say 10 to the power -2 is the same as 1/100, there's a rule of indices we're going to do in mathematics, indices, which says a to the power -m is equal to 1/a to the power m. If you have a negative power, you can convert it into a positive power by making it a fraction over 1. So if I have 10 to the power -2, I can convert it into a fraction by saying 1/10 to the power 2. Then 10 to the power 2 would be 10 times 10. So it would be 10 times 10 is 100. So it would be 1/100. So that's what, where am I? Kind of tally. Oh, it's here. So that's what I did here. So 20 centimeters to meters. I want to convert 20 centimeters to meters. This centi here means 10 to the power -2. So it will be 20 times 1/100, using this rule of indices. Therefore, this would be 20/100 100. That cancels, then it would be 0.2 meters. So do you see how this prefix table can be used to in terms of unit conversion? I'm going to be showing you a lot of examples as we do many questions in physics. So let's move on to now, let's start looking at the basic fundamental units one by one. And that's what we're going to be doing throughout the syllabus. We're going to start with length. And then next time we're going to do time. Then we're going to move back to length to do the whole motion graphs, kinematics, dynamics. Maybe you have something like this. I'm sure you've seen these questions a lot. Motion graphs, then they say find the acceleration in the first 3 seconds, find the total distance of the journey where you use the area under the graph. So that's how we're going to be moving. We're going to be picking an SI unit and studying it. And I'm going to be reminding you at each lecture that, all right, this is now this type of SI unit. So let's start with the basics. Let's start with the SI unit of length. The physical quantity, sorry. So physical quantity, length, SI unit, meter, small letter m. So length can be measured using various instruments, but the ones that they want you to focus on mostly for your exam are your meter ruler, your vernier calipers, and your micrometer screw gauge. So for all these, you have to know the right way to measure them, how to use them the right way, how to obtain measurements, Also the issue of error. When I'm using a ruler, when I'm using a vernier caliper, when I'm using a micrometer screw gauge, how am I supposed to obtain accurate measurements while avoiding errors? This is a very common question. Even sometimes, even in a practical, do you have practicals in science?
Yes.
You do, right? Maybe you might be given some, there will always be a question which says, how do you reduce the error of the given instrument in your experiment? How do you avoid error? So for each experimental design, you have to know the right way of using it, how you're supposed to obtain the given measurement accurately, and how you're supposed to reduce the amount of error of that specific instrument. So let's start off with the meter ruler. Oh, by the way, this is very important. Something known as the least count. So the smallest value that can be measured by any instrument is called the least count. So if your meter rule can only measure accurately to a, a, a point over a millimeter, that would be its least count. The least value that that instrument can measure is known as the least count. This is an extremely very important thing. Because if, for example, your vernier caliper can only measure things approximately to the nearest 0.01 centimeter, but your micrometer screw gauge can actually measure things smaller, up to 0.01 millimeters. No wonder every time we're doing our calculations using a vernier caliper or a micrometer screw gauge, we always multiply by the least count, which is 0.01. So it doesn't just come from nowhere. Oh, well, why are we multiplying by 0.01? We're multiplying by 0.01 because we have to take into account the value of error The value, because it's the smallest amount that, it's the smallest number that can be measured using that particular instrument. That's the least count. All right, so let's look at a ruler. So a ruler, practically, you know what a ruler is, right? A ruler is used to measure length, practically in distances. It can go up to a meter, sometimes a kilometer, but it usually ranges to 1 millimeter and 1 meter, centimeters, and also millimeters. To use a ruler, you have to touch the object being measured. So you place the ruler against the object being measured. Zero on the ruler must line up with the end of an object. So this, if you have a ruler like that, and you know that's the zero marking, the object that you want to measure, this zero here, has to be in line with the object. Whatever it is that you want to measure, maybe it's the length of a brick of some sort, whether you want to measure it to avoid error while you're using a ruler or any other instrument, the zero marking, this zero marking, these are free marks, by the way, any instrument which has measurements, the zero marking always has to be in alignment with the object that you're measuring. And always, when you're trying to get a reading, your eyes have to be directly over the scale. So your eyes have to be directly over the scale to avoid what we call parallax error, which is, what's my case, to avoid parallax error, which is error due to your eye perception, how you're supposed to see. Well, what do I mean by this? Let me show you a diagram. So if your measurement is here, if you're trying to measure 5 centimeters, like so, your eye has to be directly overhead your reading. Don't go to the side, you lean over to one side, you see 5 centimeters, or you start leaning over to the other side and say, oh no, 5 centimeters or 5 centimeters. No, you have to be at a 90-degree angle, directly at a 90-degree angle of your measurements to avoid this error of parallax. So how do you avoid the error of parallax? You make sure that your reading is directly above your measurement. If you don't want to say something fancy like that, you just say make sure your reading or your eyes are at 90 degrees. Your eyes should be at 90 degrees with your measurement. Remember, I showed you a 90 degrees here. The eye went, it hit the marking there of the ruler, and the ruler is on this plane here, and this angle here is a 90-degree angle. So make sure your eye is at a 90-degree angle with the reading that you want to read to avoid error of parallax. Where we all right, so let's try to have a look at certain meter rule readings here. So I don't know whether you can see this. So here we're trying to measure some form of brick. Maybe we're trying to a metal plate, right? Metal plate, and we're trying to calculate the area. So area is length times breadth. And here, this person who's been using this ruler hasn't used this ruler well, because remember, they're already making an error, because the zero marking of the ruler has to be in direct contact, with the object. But you can see here they have made a mistake, and here they have made a mistake. So we have to be able to discern. We have to be able to ask ourselves, all right, how are we going to make sense of this reading here? So we're going to start counting. So for each measurement here, our zero, we will take our new zero as here. Even here, we'll take this as our new zero, and we'll be moving 1 unit at a time. So for example, here we'll say 0, 0 0.1, 0 0.2, 0 0.3, 0 0.4, 0 0.5, 0 0.6, 0 0.7, 0 0.8, 0 0.9, 1, 1.1, 2, 3, 4, 5, 6, 7, 8, 9, 2, 2.1, 2, 3, 4, 5, 6, 7, 8, 9, 3, 2.1, 2, 3, 4, 5, 6, 7, 8, 9, 4, 4.1, 2, 3, 4. So our length will be 4.4. Multiplied by, what is our breadth? This person made a mistake. They didn't use this ruler properly. So we're going to take our 0 as there, and we start counting 0, 0 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 2, 2, 2.1, 2, 3, 4, 5, 6, 7, 8, 9, 3, 3.1, 2, 3, 4, 5, 6, 7, 8, 9, 4, 4.1, 2, 3, 4, 5, 4.5. Therefore, our area will be 4.4 multiplied by 4.5, which would be 19.8. Remember, so this length is in meters, breadth is in meters, so 19.8 meters times meters would be square meters. So that is the area of the metal plate because of the mistake that the student made. So this is an example of how an examiner might bring a question just on a rule. Observe the diagram, try as much as possible to be accurate in terms of observing the reading. You've seen this before, right?
Yes.
So this is a Vernier caliper. A Vernier caliper has got two types of jaws, because what you have to do here is you can lock an object. So a Vernier caliper practically has this big ruler here that is sort of, you can't move it. This big ruler is, you can't move it. So this big ruler here is known as the main scale. The main scale. Then you have got this other small ruler here. This big ruler also has a jaw this side. You have got this other small ruler. It's something like that. And it also has some form of measurements there. And this small ruler here is known as the Vernier scale. This small ruler can be attached to maybe one end there, and you can slide it. You can slide it back and forth. Since you can slide it back and forth, it will be able to fit in like so, with its own scale downwards, like so, with its own jaws. And you can clamp an object either there, and you can also clamp an object there. So these are known as the outer jaws, and these are known as the inner jaws. So remember, this big ruler, you can't move it. No wonder it's called the main scale. But this smaller ruler here, it's movable. No wonder it's called the Vernier scale. So every time when making readings on a micrometer screw gauge, you first have to start with your main scale reading, then you add it with your Vernier scale reading multiplied by the least count, which is 0.01 centimeters. So this is the basic structure of the Vernier caliper. you have got this fixed jaw here with this fixed jaw because it's connected to this main scale there. And you've got this movable jaw. So these together becomes the inner jaws, outer jaws. This is the main scale, the big ruler, and that's your Vernier scale. And you can move it back and forth to sort of tighten up the object that you want to measure. So how do we use a Vernier caliper? How are we supposed to use a Vernier caliper? So this is the formula for your Vernier caliper, formula number 1. Length that you're supposed to read on a Vernier caliper is what is on your big ruler, your main scale reading. That's what's on the big ruler. Then you add it with open brackets. You go on your Vernier scale. So this will be your Vernier scale reading multiplied by the least count of the Vernier caliper. The least count of the Vernier caliper is 0.01 centimeters. So whatever reading there that you're going to get on your Vernier scale, you're going to multiply it with the reading on the, you're going to multiply it by the least count, which is 0.01. So always remember this formula. Every time you see a Vernier caliper, you go down on your answer sheet and say length, whether it's on a multiple choice question or a paper 2 type question, you go on your Vernier caliper and say length is equal to main scale reading multiplied by open brackets, Vernier scale reading plus the least count. Then you start substituting. Let's look at an example. Oh, and by the way, to avoid error, your Vernier caliper has to look like this before making your measurements. So you have to make sure that the main scale, that's the main scale, your main scale, your big ruler, and your Vernier scale are in alignment. So you've seen this 0 on your main scale and this 0 on your Vernier scale are in complete alignment. So before you use your Vernier caliper, you have to zero it. This is what it means when you say zero your Vernier caliper. Is your main scale and your Vernier scale are the zeros in alignment. That's what's called a zero in your Vernier caliper to avoid errors. There are 2 types of errors that you can make using a Vernier caliper. When your Vernier scale reading, when your 0 is after this 0 of the main scale reading, that's a positive error. Because remember, on your number line, if you go this side of the number line, it's at the positive side. So if this got 0 here, it's not in alignment, but it moves that side. It's a positive error or a positive 0 error. And this other error, remember, when you're moving on your number line on the other side, it's the negative side. So if you put your Vernier caliper like this, where these zeros are not in alignment, but the Vernier reading, the Vernier caliper, you've moved it on the other edge of the main scale, you're going to make a negative 0 type of error. So these are the 2 errors. And how do you avoid these 2 types of errors? You make sure that your main scale, so this is your main scale 0, and your Vernier scale 0 are in alignment. These 2 zeros have to be in alignment before you make any type of reading. For example, our Vernier caliper here, these zeros here are definitely in alignment right here. So this is a good Vernier caliper. So let's solve some questions. So this is a good Vernier caliper you've seen, an excellent Vernier caliper. You've zeroed the Vernier caliper. No 0 error is the precise arrangement of the meter scale and the Vernier scale so that the zeros on both scales fit each other like so, then you can now take precise measurements. We have to ensure that the caliper we are using is of no zero error. No zero error means you have to zero your vernier caliper. Make sure that your main scale reading and your vernier scale reading zeros are in alignment. So now let's look at a question on how we are supposed to, so it's an exam question. You've seen maybe a question like this before, and they say, all right, this is the vernier caliper. Sometimes they won't even show, okay, they won't show you a nice diagram. Sometimes it will just be a simple diagram like this. And how do I know that this is the vernier caliper? Because it has got two scales. There's a scale above here, which is the main scale, and there is another scale just below there, which is the vernier scale. So every time you have got a vernier caliper reading, you have to be very, very careful to know, because it will just be a small section. So you have to be careful to know, all right, where my readings coming from. And in the exam, remember physics, especially if it's paper 2, they will not just mark your final answer. If it's ECZ, they won't mark your final answer only. Remember, you want to maximize your chances of getting marks in the exam. So you first tell your examiner that you know the formula to use when you have a vernier caliper. You tell them that length given a vernier caliper is your main scale reading multiplied by, open brackets, vernier scale reading multiplied by the least count of the vernier caliper, which is 0.01 centimeters. So how do we obtain the main scale reading? The main scale reading is the reading just before the zero marking on the vernier scale. So that's the vernier scale there, the zero marking. Before this zero, there's this measurement there. So this is the measurement that we're looking for there. That's the main scale reading. So how do we get the main scale reading? You go to the vernier scale, then you look above, you're like, all right, there should be a reading before this zero. That would be the main scale reading. So this is the main scale reading that we're trying to look for there. And you see that this is 9, right? All right, this is 9. So how did we get to 9? Probably this is 9, 9.1, 9.2, 9.3, 9.4, 9.5, 9.6, and so on. So because here we got to 9, so what measurements could this be here? What measurements could this be here? So we start going backwards. So I'm sure this was 9, probably this was 8.9, then this was 8.9, then 9, you see, right? 8.99. So if we're going behind 8.9, this would be 8.7, this would be 8.6, this would be 8.5. So 8.5, 8.6, 8.7, oh, 8.6, 8.6, 8.7, 8.8, 8.9, 9. So this reading here, the reading just before the zero marking on the vernier scale should be 8.6. So here we'll say 8.6. That's our main scale reading. So how do we get our main scale reading? The main scale reading is the reading just before the zero marking on the vernier scale. We go on our vernier scale, we identify the zero, then we look at this reading here before the zero marking. That's the main scale reading. And we look at our scale, we try to figure out, all right, how did they get to 9? So maybe one line here represents 1 unit. So if I go 8.6, 8.7, 8.8, 8.9, 9, 9.1, 9.2, 9.3, 9.4, 9.5, etc. So here it's 8.6 multiplied by open brackets, the Vernier scale reading is the reading that's in direct alignment between the main scale reading and the Vernier scale reading. So you start looking at the one that's in alignment. So you've seen here, this and this are in perfect alignment. So this becomes the Vernier scale reading. The Vernier scale reading is this one here, because you look for a value where the main scale and the Vernier scale are in perfect alignment. So we have to figure out what this reading here is. So we go to the Vernier scale and you're like, we've gone from 0 to 5 there, and we've also gone from 5 to 10. How are they moving here? Are they maybe saying, all right, maybe this is 5, 6, 7, 8, 9, 10. So can they say maybe 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10? So they're moving 1 unit. So the Vernier scale is moving 1 unit. You've seen that, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the reading here that's indirectly in alignment, where the main scale and Vernier scale are on the Vernier scale, is 2. So that's the 2 that we're looking for. So we're going to put the 2 there, but we won't just say 2. We're going to multiply this 2 by the least count. And what's the least count of the Vernier caliper? 0.01. So that's our equation, and this is how we are substituting. But this has to be addition there. There should be an addition symbol here. I think I've made a mistake in my formula. Yeah, there's an addition symbol here. Yeah, it didn't look right. Okay. So let me just change this symbol here to an addition symbol. Okay. Length is the main scale reading plus open brackets Vernier scale reading multiplied by the least count. So our main scale reading, how did we get the main scale reading? That was our main scale reading. We went on our 0 here on our Vernier scale, and the reading just before became the main scale reading, and that was 8.6. Then how did we get the Vernier scale reading? We started scanning our main scale and Vernier scale until we found this here that's in perfect alignment. Then we looked at how the Vernier scale is going. All right, 0, there's a 5 there, there's a 10, so maybe there's 1 unit, 5, 6, 7, 8, 9, 10. You have to be critical when thinking, and when you practice a lot of questions, you become good at this. So maybe it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, meaning this one here is a 2. So that's my Vernier scale reading. So where there's Vernier scale reading, we substitute it with a 2. Then we multiply it by the least count, which is 0.01. Then the rest is just algebra. The rest just becomes algebra. You have to add there. The formula says we add. So the rest becomes algebra. So we say 8.6, we add it with, what is 2 multiplied by 0.01? 2 multiplied by 0.01, you even get your calculator, because physics, we use calculators. You find your answer as 0.02. Then you add 0.02 plus 8.6. Then you'll realize that, all right, my reading is 8.62 centimeters. And that's how you read units on a Vernier caliper. You have to be able to pause, rewind this video, watch this video over and over for you to really understand. You're going to do that, right?
Yes.
All right, make sure you watch this video. So let's look at another instrument known as the micrometer screw gauge. The good part about this instrument, the examiners, I don't know why they love this instrument. They like to bring a question which says you have to first label it. You identify the instrument, you identify it, you tell them, all right, this is a micrometer screw gauge. Then they will say, label the following parts. So practically a micrometer screw gauge, it's like a screw. You can sort of screw, you spin it, and you sort of lock the object. So they might bring maybe actually they can bring a physical diagram like this, and they say label it, but ECZ, they sort of, we print our exam papers in black and white. So I'm sure they are going to draw a possible diagram. They can draw some form of diagram, something like this. They can draw some form of a simple diagram there. And they say, identify this instrument and say, right, this is the micrometer screw gauge. You've identified them. Then they say, label A, B, and C. So this here on a micrometer screw gauge, it's like your main scale, but they call it the sleeve reading. And then here is your main scale reading. So you have got your sleeve reading and your main scale reading, which is like an umbrella-like structure. So this will be your main scale reading. And here this is something known as a ratchet. The ratchet makes sounds because if you put your object there and you start twisting the sleeve, so you start twisting this, you roll it round. As you're rolling it round, this object here will start getting tightened between these two points there. It will start getting tightened by this structure here known as the spindle, because as you are spinning, it's also spinning. It's going round to tighten the object. No wonder it's called a spindle. As it's sort of tightening up the object, sort of rounding it up, it gets tighter and tighter. And when it's too tight, the ratchet will start making sounds. It will go like ta, 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 ta. Then you'll be like, oh, all right, I think I'm ready to now take the reading of the micrometer screw gauge. Oh, by the way, going back to the Vernier calipers, sorry to take us back. I just remember there's something I forgot to mention. They might say, give an example of the type of things that you can measure using a Vernier caliper. Vernier calipers, you can measure diameters. So let's say I have a measuring cylinder there, and I want to know the distance between that circle and the edge of that circle. That's known as the diameter. So I can get my Vernier caliper using the outside jaws. I can clamp it from there, and I can clamp it there, and I can know the diameter of my measuring cylinder. So this is a good example. And they say, all right, give one example of an application of using a Vernier caliper. Then you can say, all right, measure the internal and external diameters of like circular objects. For example, your measuring cylinder. But for this one, you can have a very thin wire. Like a very thin wire, like so, very thin wire. Maybe you picked up a wire and you want to measure the diameter. You can actually measure the diameter because it's the micrometer screw gauge. It's in millimeters. So all the time you are giving your answer for a micrometer screw gauge, it has to be in millimeters because that's the least count of a micrometer screw gauge, 0.01. And know the parts. So when you get these notes, I want you to draw this diagram. Even if it's a live picture like this, draw it and know all the parts, all right? This is the ratchet, etc. And also know the functions of these given parts. So used to measure very small distances, used to measure very small distances, and the least count is 0.01 millimeters. You can determine even the diameter of a wire. So diameter represented by D of a wire. So you just place the wire between the anvil and the spindle ends to indicate indicated in the diagram. So you're placing the object between the anvil and the spindle, and then you rotate the spindle. Remember, rotate the thimble. So you're rotating this part here. So you rotate the thimble unit until the wire is firmly held between the anvil and the spindle. So this is the anvil there, the end, and the spindle. The ratchet is provided to avoid excessive pressure on the wire. It prevents the spindle from further movement, squashing the wire. So it will give you a warning sound. Ratchet, it will be like, tick, 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 tick. All right, okay, meaning it's ready. We're now ready. The object has been held firmly, meaning now we're able to take the measurement. So how do we take measurements using the micrometer screw gauge? More or less the same with the Vernier caliper, but for a micrometer screw gauge, we're going to get our sleeve reading, then we're going to add it with our main scale reading, multiplied by our least count, which is 0.01. But remember, Vernier caliper, 0.01 centimeters, micrometer screw gauge, 0.01 millimeters. So here's an example of a question. So here, this part here, remember they'll bring a diagram like this. This is the sleeve reading. And then this part here is the main scale reading for a micrometer, main scale reading. So if we have got a micrometer screw gauge like this, we're going to say the reading will be, so the length of the micrometer screw gauge will be the sleeve reading. So I'll put it as SR, the sleeve reading, plus our main scale reading, MS, multiplied by our least count, which is 0.01 millimeters. So here our sleeve reading, this is a 0.5. So this is 0, 0.5, 1, 1.5, 2, 2.5. So our reading here is actually 2.5. So our sleeve reading is 2.5. We're adding that 2.5 with our main scale reading. So we look at our reading here. And how do we identify our main scale reading? We follow our sleeve reading like so. It will be this reading here that's in alignment, where the sleeve reading and the main scale reading are in proper alignment. So how, okay, we're at 30 here, we're at 35, then we're going to 40. How did we reach 35? Maybe they are saying 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. All right, that's how we are going. So this reading here, that's in alignment with the sleeve reading and the main scale, is probably 36. Then you go there, all right, my main scale reading is 36, and then we're going to add, multiply it. We're going to multiply that with our least count of the micrometer screw gauge, but this time it is 0.01 millimeters, remembering our units. So multiplied by 0.01. So we'll say this is 2.5 plus, we get our calculator. By the way, this question is asking for something else, but here we're trying to get the reading. We're going to read the question later. So we say 36 multiplied by 0.01 to be 0.36. Then we add plus 2.5, meaning our micrometer screw gauge reading will be 2.86. That's our millimeters. That's our answer. But let's read the question, right? The question says the diagram shows part of a micrometer screw gauge. What is the smallest reading that can be achieved using this micrometer screw gauge? What is the smallest reading that can be achieved using this micrometer reading. They are asking for the least count of a micrometer screw gauge. So what is the least count? The least count LC is what?
0.01.
Millimeters, right? Exactly. So we go to our multiple choice here and say, all right, our answer is 0.01 millimeters. If someone who wasn't taught what a least count is, they won't be able to understand this, because they'll be like, they'll try to use the diagram to solve the question, and they'll keep on finding weird answers and their answer won't be there. But for you who's been taught, you've been taught that, all right, every instrument has a smallest numerical value that that instrument can measure. And that is known as the least count. So the least count of the vernier caliper is in centimeters, 0.01 centimeters. But the least count of the micrometer screw gauge, because it can measure even smaller objects, it can even measure even smaller objects, it's 0.01 millimeters. We are together.
Yes, but I'm behind.
Where?
Where did you get 2.5?
All right, the 2.5. So remember, we have a certain formula that you have to write down. So let's get the reading of this instrument. Let's try to get the reading of our instrument on our micrometer screw gauge. So the micrometer screw gauge has got two parts. This is a simple diagram here. This right here is known as the sleeve, and this right here is known as the main scale reading. So we're going to say length is equal to our sleeve reading plus, open brackets, main scale reading multiplied by our least count, which is 0.01 millimeters. So our sleeve reading is here. So this is 0. Every point is a 0.5. If you see like a big number, a small number, a big line, a small line, a big line, a small line on a micrometer screw gauge, it's a 0.5. It's a 0.05. So this will be 0, 0.5, 1, 1.5, 2, 2.5. So our reading is there. So this is the main scale reading of our micrometer screw gauge, which is 2.5. You've seen that, right?
Yes.
Then we're going to add it with our main scale reading. How do we get our main scale reading? Our main scale reading is the reading that is in alignment between our sleeve and main scale. So it's this one here. This reading here is that it's in proper alignment between our main scale, which is from there to there, and our sleeve reading here, which is from there to there. So it's this reading here. So we're trying to figure out what's that reading. Okay, how is the main scale going? There's 30, 35, 40, maybe one unit represents one line represents 1 unit. Let's try that. 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. All right, so this unit that we're looking for is 36. So our main scale reading is 36. Then we multiply it with our least count, which is 0.01 millimeters. We get our calculator and we say, all right, 36 multiplied by 36 multiplied by 0.01, it's 0.36. Where's my cursor? So that would be 2.5 plus 0.36. We add them together plus 2.5. Our answer will be 2.86 millimeters as the reading on our micrometer screw gauge. So just make sure, keep on watching this video, pause it, rewind, solve it. Have you been watching all the videos we've done so far? Have you been watching all the videos we've done so far?
Yes.
All right, thank you. Just keep on watching them. They'll be very important for your exam. All right, so let's look at measuring liquids. This is particularly important because, you know, liquids have got a fixed volume, but no fixed shape. So the best instruments that we can use to measure liquids are known as cylinders or graduated cylinders. Graduated cylinders, it means they have a maximum volume. So at times you can have measuring cylinders that are graduated up to 100 cubic centimeters, and some measuring cylinders can be graduated maybe to 25. Volume is in cubic centimeters. 25 cubic centimeters or so. So that's how we measure volume of a liquid. We use instruments known as measuring cylinders. So this is how a measuring cylinder here looks like. So this measuring cylinder is graduated at 250, meaning its maximum capacity is 250 cubic centimeters. Including this one. So these are also different types of graduated cylinders, and you have to be able to know how to read the units of these graduated cylinders. So this one here, they are saying 100 to 10. It means it's going like 10 to 20, 30, 40, 50, 60, 70, 80, 90, 100. This one is saying its maximum capacity is 250 to 5, meaning it's going 5, 10, 15, 20, 25, etc. This one is going in tools. So these two are going in tools. So at times you have to be very careful. And also when you are looking at, maybe there's a diagram there, all right here. So maybe you are in chemistry and there's a titration, like so. This umbrella-shaped structure, a downward dome, is known as a meniscus, a meniscus. So you're reading, you know, there's gravity here on Earth, right? There's gravity. So because of gravity, gravity pulls this water downwards in this measuring cylinder, forming a dome-like structure, a downward dome called a meniscus. So our reading has to be directly below the meniscus. So our eye should be there, and we take the reading that is below the meniscus. So read here, your eye has to be right there. That's the reading. Unless if it's mercury. Mercury has the ability to define gravity. So mercury, the meniscus is going to look like that because it can defy gravity. But not water. Water, gravity will act on it, so the meniscus will be downwards. We're going to see an example of mercury when we start looking at the topic of pressure. Then we say, all right, pressure is a force per unit area, and we'll see how we can calculate atmospheric pressure, etc., given certain circumstances. But when reading volumes, your reading has to be directly below this meniscus there. Again, to avoid error of parallax, this is what I was explaining. Always look straight from the side of the meniscus, like so, this arrangement, to know the volume. So what instruments can be used to measure volume of liquids like water? A measuring cylinder. To avoid error of parallax, be in alignment. Again, make that 90-degree angle. That's your measuring cylinder. That's your meniscus. Your eye is going like that. The measuring cylinder is like that. This makes a 90-degree angle. So your eye should always be at a 90-degree angle to whatever unit that you are trying to measure, to avoid error of parallax. All right, again, this is the examples I was giving you. For water, the meniscus will be down below, but B is mercury because mercury defines gravity, so you read the meniscus above the line. So here your eye will be there, But for Mercury, your eye will be above because Mercury is able to defy gravity. All right, so time, we're almost done. This is our last part. So time, SI unit. The SI unit for time is seconds, right? And these are various examples of instruments that can be used to measure time. For example, an analog clock, a digital clock, another analog digital. So you can either use an analog clock or a digital clock to measure time or time intervals. So let's just solve this question here. Can I expand this so that you see it properly? Can I zoom in? I can zoom in. All right. I'll read it for you so that you can see it properly. Let me use this highlighter. So this is what's this? A digital clock. So we have a student uses a stopwatch to time a runner running around a circular track. A student uses a stopwatch to time a runner running around a circular track. The runner runs 2 laps. So the runner runs 2 laps around this track, twice around the track. The diagram shows the reading on the stopwatch when the runner starts running at the end of the first lap and at the end of the second lap. What is the time taken for the runner to run the second lap? So every time we're calculating an interval. An interval is always calculated as the final time that you ended with minus the initial time that you began with. So our first lap here, it was 1 minute 13 seconds minus 00 seconds. So he ran the first lap in 1 minute and 13 seconds. But the question is saying, what is the time taken for the runner to run the second lap? So the second lap was in 2 minutes and 3 seconds. So we have to know the given time interval there. So it has to be 2 minutes and 13 seconds minus 1 minute and 13 seconds. So how do we subtract time? We'll say 2 minutes and 0.3 seconds minus 1 minute and 13 seconds. So 3 minus 3, it's 0. But 0 minus 1, it can't, right?
Yes.
So we're going to borrow, but by the way, in time, we don't borrow ones, we borrow minutes. So if we borrow a minute there, 1 minute is 60 seconds. So we're borrowing 60 seconds there. So we have to add this 60 there, such that this time here will be 60 plus 3. So we'll now have 63 minutes this side. Therefore, this question is now going to become 1 minute and 63 seconds. 1 minute and 63 seconds subtracted from 1 minute and 13 seconds. That's how this question is going to be, because we've borrowed 1 minute from there and we've added it with the 3 seconds that we had there. So it will be 60 plus 3. It will give us 63 seconds. So we've changed the time from 2 minutes and 3 seconds to 1 minute and 63 seconds to accommodate this one there, because at first it was 0 minus 1. So we can't do anything. So we borrowed a minute to change the time in a manner such that we can subtract it properly. So we've gone from 2 minutes and 3 seconds to 1 minute and 63 seconds because we borrowed a minute, right? We're together.
Yes.
So we can now easily subtract 3 minus 3, it's 0. 1 minus 6 minus 5, or 6 minus 1, it's 5. Then here 1 minus 1, it's 0, 0. So the answer will be 0 minutes and 50 seconds. So he took 50 seconds to run the second lap, which is here. So he was faster the second time he was running. So this is our final answer. So just to rewatch the video, make sure you watch, revise, pause, know your basic units, know your derived units, know your SI units, know how to use Vernier caliper, know how to use micrometer screw gauge, know certain time calculations, know your prefixes, know your dimensional analysis, start knowing your formulas right now so that physics should become very, very easy. The more you practice this, the better you're going to become. So next time we're going to look at the simple pendulum, certain types of questions that can come. What is period of a pendulum? What is frequency of the pendulum? What type of experiment can we use to find the period of the pendulum as accurate as possible? So that's what we're going to do next time when we do physics. As usual, please make sure you watch this video, write all these notes in your book. I'm going to send them right now via email. I'll end the class and I'll see you in the next class. Well, okay?
Okay.
All right, let me just send the notes. See you in the next class. Bye.
Okay.